Good day, we'll be discussing Chapter 5, the mathematics of graphs. Now, what is a graph? A graph is a collection of points. So, when we talk about points, it looks like a dot or just plainly like this. So, it depends. So, it's a collection of points called vertices or nodes, and line segments or curve called edges that connects the vertices. So, say for example, if we have these two nodes or vertices, an edge looks like this. It's either a curve or a straight line. Okay, so we can draw it like that too. So edges can be lines, straight lines, or curves. So for example, consider the graph on this side. What are the vertices? The vertices are A, we have B, we have C, we have D, and we have vertex E. Okay, what are now the edges? The edges, we have this one, AB or BA. We have BC or CB, BD or DB, CD or DC. We also have CE or EC. And lastly, we have DE or ED. Okay, so these are the edges. Now, graphs can be used to illustrate huge connections such as social networks on FB, flight destinations of airlines, the simple community garbage collection route, or even the computer system connectivity in a school. So we can consider the flight destinations as or the cities as our vertices, and their connections is the of course the direct flights. For the social networks on FB, of course, if you are friends, then of course we can create a line from you and your friends. So example in constructing a graph. So let's consider this. So the following table lists 11 cities connected by Cebu Pacific airline flights. The check symbol indicates that the cities have direct flights. So meaning we will be constructing a graph. So in constructing this information, we will consider the cities as our vertices, and the check mark will be our edges. The direct flights will be our edges. So say for example, we have here Manila. So Manila has a direct flight to Tokyo. So this one to Tokyo. So Manila, we have this. So Tokyo. Next, we have to Seoul. We have to Taipei. And we have to Hong Kong. No, not that one. To Hong Kong is this one. And then to Macau, to Bangkok, to Ho Chi Minh, to Kuala Lumpur, and to Singapore. That's why we have these connections. We connect them from Manila and the other countries or cities. Next, we have Tokyo. So here at the top, Tokyo is or has direct flights to Manila. So we have this one to Seoul. So that's why we have this connection, and then to Taipei. So that's why we have this connection. Next city, we have Seoul. So Seoul. So here's a top. Here is Seoul. Seoul is connected or has a direct flight to Manila. So we have this one. Next is to Tokyo. So this one. And then to Taipei. Where is Taipei? Taipei is actually this one. And then to Hong Kong. And so on. So you just make lines to show that the two cities have direct flights. So in short, this is now our final graph for the given information. So if you notice, Manila vertex has 9 edges. Okay, if you count this one, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Hence, it has the most direct flights. So it has 9 direct flights to be specific. Macau, on the other hand, where's Macau? This one. Macau is connected only to one node. Hence, it has the least direct flights. Okay? But of course, we have Brunei. Here, the lone Brunei. Brunei is not connected to any node. Hence, it does not have any direct flight to any of the 10 cities. Okay, so this is now our graph. Another example is this. So an X in the table below indicates corresponding people are connected on Facebook. So we have Amy, Belle, Chris, Dan, Efren, Francis, and Gina. So the instruction is draw a graph in which each vertex represents a name and an edge connects two vertices if the two friends are connected on Facebook. So let's have this illustration on the right side. Okay, so we have here Amy and Belle are connected. Okay, Amy and Dan are connected. Amy and Francis are connected. Next, we have Belle and Amy. So we're done. Amy and Belle. Belle and Chris. Then we have Belle and Efren. So we have a connection here. And then we have Belle and Gina. Next, we have Chris and Belle. Chris and Belle. So we're already done with Chris and Belle. So this one, this is already done. Chris and Belle. Then we have Chris and Dan. Chris and Francis. Next, we have Dan. Dan and Amy. So we're done. Dan and Chris. Dan. Dan and Efren. So we have this. And then Dan and Gina. Next, we have Efren and Belle. So Efren and Belle, done. Efren and Dan. So we're done. Efren and Francis. So we have this Efren and Francis. Next, Francis and Amy. Francis and Chris. Francis and Efren. Francis and Gina. The last one, we have Gina and Belle. Gina and Dan. And Gina and Francis. So therefore, this is now our graph for this one. So they look the same. Now let's go to some definitions. So when we say a loop, it's an edge connecting a vertex itself. So look at this. So it looks like this, a loop. We have a vertex and it has an edge that connects to itself. So an edge connecting a vertex itself. Okay? So you can do that. Say for example, we have this. Okay? We can have this. This is a loop and this is another loop. Multiple edges if two vertices are connected by more than one edge. So therefore, if we have two vertex and connected an edge, if we add another edge connecting these two vertices, then we call this now as multiple edges. So more than one, take note, more than one edge. So the multiple edges here is here, and this one is on this part. Okay, next. Simple graph. A graph with no loops and no multiple edges. So this one is not a simple graph because it has a loop and at the same time also it has a multiple edges. Okay, and simple graph looks like this. So if there's no multiple edges, only loop, I think that's also not a simple graph. So a simple graph is a graph that has no loop and or has no multiple edges. What is a path? A path is an alternating sequence of vertices and edges. A graph that can be drawn so that all of its vertices and edges lie on a single straight line. And any list of edges that you can trace with your pencil without picking it up. So, so we can draw a path like this, okay? Or you can draw a path like that, okay? As long as it's alternating sequence of vertices and edges. Now, if you notice this one, I start and ended on this vertex, so it's still a path. So we call this one a closed path, okay? Because it starts and end with the same vertex. Okay, so these are just some examples of a path. When we talk about path, it's not necessarily that when you draw a path, it's always a straight line. Okay, you can draw it like this, a star, or like a ladder. Okay, it's still a path. As long as you can draw this one in this manner. If you can redraw this one in a horizontal manner or without lifting your pencil. A connected graph is a graph or is a graph that is connected, that if there is a path connecting all vertices. Okay, so these are some examples. Now, if you look at this, say for example, this G1 and G2, let's say for example, this is now a graph. This is not a connected graph anymore. Okay, why? Because if you notice, these two are not connected. Remember, a graph is connected if there is a path connecting all vertices. Okay, so this one is a disconnected graph or a null graph. This one is also a null graph or disconnected graph. This is also a disconnected graph. But if we have this is now a connected graph because all of the vertices are now connected. Now, is this a connected graph? No, because we have a lone vertex. Now, let's go to a circuit. A path begins and ends with the same vertex. So this is now a closed path. A circuit is a closed path. Why? Because it begins and ends with the same vertex. So as one of my example is the star. Okay, look at this. This is a star. I started here and I ended here. So this is a circuit. A star is a circuit. So a circuit has no repeated edges. So it has no repeated edges. Take note of this. But may have repeated vertices. So for example, consider this one. Okay, so we have this circuit. A circuit, for example, on this one is this part. Okay, we have B, C. So this is the first one, BC. Then after C, we go to G. And then we go to H. And then we go back to B. So in this case, we did not repeat any edge. And we start and ended with the same vertex B. Okay, so that is the first example. Now the second one. So we started with H, so that is the first one, and then go to B, C, D, E, F, to C again, and to G, then to H again. Okay, so this is now our circuit. Okay, take note, we can repeat the vertices. So C can be repeated. Only the edges can't be repeated. Okay, and it's a circuit because it started here and it ended here. Another term, we have the adjacent vertices. Two vertices are adjacent if there is an edge joining them. So say for example A, the vertex or vertices adjacent to A is or are B and H. Okay, that is why we have edges AB and AH. Next, for B, adjacent for B, we have A, we have H, and we have C. Okay, and adjacent for C, we have now B, we have D, we have F, and we have G. Okay, two vertices are adjacent if there is an edge joining them. Now let's go to the degree. The degree of a vertex is the number of edges attached to it. Now look at A. How many edges? We have 1 and 2. So the degree of A is 2. For letter B, vertex V, vertex B, how many edges attached to it? We have 3. 1, 2, 3. Vertex C, we have 1, 2, 3, 4. So that's why the degree of C is 4. D 1 and 2, E 1, 2, F 1, 2. So all of these three vertices have degree 2. Also with G. Now vertex I has a degree 1. Now can you draw these graphs without lifting your pen and without passing through edges twice? Yeah, what is one? So let's try. Can we start here? No. We cannot start here. So let's start here. Okay. So I started here and I ended here. So check. How about this? Da, 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 da. Okay, so check. So next we have this. 1, 2, 3, 4, 6, 7, 8. Da, da. Mhm, mhm. Okay, so you have this. So I started and ended on this vertex. Okay, so this is check. Now these two are examples of which we cannot draw this one without lifting our pen. Now who is the founder of graph theory? Now graph theory is a branch of mathematics that was developed after Leonhard Euler. He is a Swiss mathematician. He solved an 18th century problem involving the seven bridges of Königsberg in Old Prussia, now Kaliningrad, Russia. Now this city has four districts divided by the Pregel River. So looking at the picture, we have now these four districts, the A, B, C, and D. And if you notice, we have these yellow lines. These are the seven bridges. So these seven bridges connects these four districts. Now in Euler's time, people were puzzled if there is a travel route that would only cross each of the seven bridges exactly once. Okay, so exactly once. Now, Euler proved in 1736 that this is impossible. So actually, that graph can be redrawn into this form. Okay, so these are the uh, districts, and these edges here are the bridges. Okay, so according to Euler, it's very impossible for a travel route to exist in which we only cross a bridge once. No, it's very impossible. So going back, in connection to this, we will now discuss Euler paths and circuits. Now, an Euler circuit is a closed path. Take note, a closed path. When we say a closed path, it must start and end with the same vertex. Okay? So a closed path that uses every edge. It uses every edge, meaning it passes through every edge, but never uses the same edge twice. And take note, since it's a closed path, so it starts and ends with the same vertex. Now, in an Euler circuit, the path may cross through vertices more than once. So for the edges, it must be once, but for the vertices, you can pass or cross this one a multiple times, for multiple times. So say for example, we have this. Does this contain an Euler circuit? Of course, so we have this example. So this is one. So this is one to A to E. Then we go to C. Then we go back to A. Then we go down to B. We go to C, F, E, D, and A. We started here and we ended here. Take note, we did not cross or use an edge twice. Okay? But of course, when it comes to vertices, we have used some of the vertices more than once. So our work concern here is only the edge, that the edges must be crossed or used once, exactly once. So examples of Euler circuit are these two. Now in the Königsberg's bridges problem, finding a path crosses each bridge exactly once and returning to the starting point is the same as finding an Euler circuit in the graph below. And this is impossible according to Euler. Now, additional examples. Which of these have Euler circuit? So you may pause the video if you want to solve this activity. Okay, so we have these answers for G1. We start with A, then to B, to E, to D, to C, to E, to A. So it's an Eulerian circuit. We started and ended with A. For G2 and G3, there is no Eulerian circuit. But if you can find an Eulerian circuit, feel free to comment. And for the last one, of course, we have this, a star inside. So A to D, to B, to E, to C, back to A, and then E, D, C, B, back to A. So we started and ended with A. So in finding Euler circuits, it is not, say for example, for the arrangement, it is not unique because you may start in different vertex or vertices. Okay, so it's not unique. So in my case, I started with A, and this one also I started with A. So in this graph number 1, so you may start with B. You may start with C or D. In this case also, for this one, you may start with any vertex. Okay, so these are the Euler circuits. Only two, graph 1 and graph 4 only. Now we have a theorem that will tell us if a graph is Eulerian or not. So a connected graph is Eulerian, meaning if when we say Eulerian, it has an Euler circuit. So a connected graph is Eulerian if and only if take note of this, every vertex of the graph is of even degree. Now going back to our example, so look at this. Every vertex has an even degree. This one, take note, 3 is not even, so it's not Eulerian. The same is true with this. Okay, so that's why these graphs 2 and 3 are not Eulerian because they don't have Euler circuit. For the last graph, this one, all of the vertices have 4 or degree 4, then of course, this is Eulerian. Okay, so if the instruction is determine whether the graph is Eulerian or not, so you may use this theorem. So your answer will be yes or no, and then you cite this theorem. But if the question is give the Euler circuit, then of course you must do it like this one. Okay, because the instruction is give the Euler circuit. If it says determine, then you will use this one. Determine if it's an Eulerian graph or not. Okay, so in this one, Königsberg again, so we have no Eulerian circuit because the vertices have degrees 3 and 5, which are odd. They're not even. Now let's go to path. An Euler path is a path that uses every edge. Again, it's every edge in the graph once, but it does not start and end at the same vertex. Okay, because if it start and end at the same vertex, we now call it an Euler circuit. Okay, so in short, by definition, every Eulerian circuit or Euler circuit is an Euler path. Okay, because by definition, Euler circuit is a closed path. So it's still a path. So again, every Eulerian or Euler circuit is an Euler path, but not the other way around. No, but not every Eulerian path or Euler path is an Euler circuit. Why? Because a path may not start and end at the same vertex. So therefore, not every Eulerian path is an Eulerian circuit. So determine whether the given graph is Eulerian. If it is, find an Eulerian circuit. If it is not, can you find an Euler path? So let's answer first the first question. Determine whether the given graph is Eulerian. So it says determine, so we'll just use the Euler theorem. According to the Euler theorem, in order for it to be Eulerian, the degree of the vertices must be even, all of them. But in this case, if you notice, look at 3, A, vertex A. The degree is 3, which is not even. So therefore, by the Eulerian graph theorem, this is not Eulerian, meaning there is no Eulerian circuit. Now let's go to the last one. If it is not, so it is not, so there's no Eulerian circuit. Can you find an Euler path? So let's try. So I'll start with A, then to B, then to C, to D, to E, to F, to G, to H, I, J, and then back to D, then down to G, go to A, L, K, J. Okay, so this is now our path. Take note, it did not start and end with the same vertex. Okay, so I started with here with A and then I ended up with J. Okay, it's an Eulerian path or Euler path because I've used only the edges once. Now, find an Euler path if it exists. Now, for A and D, take note that for A and D, these two are already are already Eulerian circuit or Euler circuit, so it has an Eulerian path. So like this. Okay, A, B, E, D, C, E, A. So we still have A, so it's a closed path. Okay, and this one we also have A. Okay, next for letter B, we have this path. So let's follow A, B, C, F, A, E, D, C, E, F, B. Okay, so that is our Euler path. It does not start and end with the same vertex, so it's an Euler path. Another one, so we have, let's start with C, E, D, C, B, A, D, E, and then A. So it's an Euler path. And this one, if you notice, the degrees are all even. This is 2, the degree of this is 4, degree is 4, degree is 4, 2, and 2. So this is basically an Euler circuit. Okay, so this is now our path, a closed path, because it started and end with the same vertex. So we have B, A, D, F, E, D, B, C, E, B. Okay, that's our Euler path. And at the same time, an Euler circuit. Last, we have this. So D, A, B, C, D, E, A. So this is now our Euler path. Again, Euler paths and Euler circuits are not unique. So you may find other Eulerian path or Euler path. Now, to determine whether it's an Eulerian path or not, or a connected graph contains an Eulerian path, then of course you may use the Euler theorem, Euler graph theorem, and at the same time, or you can also use this Euler path theorem. The Euler graph theorem is on the that every vertices must have even degree. Okay, but for Euler path theorem, a connected graph contains an Euler path if and only if the graph has two. Take note, has two vertices of odd degree. So only two vertices have odd degree, and the other vertices have even degrees. Furthermore, every Euler path must start at one of the vertices of odd degree and end at the other. Okay, looking at this, our previous examples. So specifically this one, B, C, and D, we use the Euler path theorem to show that these three graphs have Euler paths. And E uses the Euler graph theorem because it's an Euler circuit and all Euler circuits are Euler paths. Okay, so these are the paths. Now, application of Euler path theorem or um, Euler path theorem, or maybe you may use Euler graph theorem. A biker would like to traverse all trails exactly once. So consider the graph on the right side. Is it possible for the biker to plan a trip that traverses all the trails exactly once? So this means that we are asked to find or to give the Euler path. Okay? And letter B, is it possible for him to traverse all the trails and return to the starting point without repeating any trail during the trip? So, meaning it will start and end with the same point. So it's now an Euler circuit. It's not a path. Okay, so let's look at the degrees. So the degree of A is 3, the degree of B is 4, the degree of C is 4, the degree of D is 2. So we have D here. So we have two edges. The degree of E is also 2. The degree of F is 4. The degree of G is 3. So if you notice, we only have two vertices with odd degree. So by the Euler path theorem, we can say that this graph, that it is possible for the biker to plan a trip that traverses all the trails exactly once. Okay, so because it has an Euler path. So the answer is yes, it is possible. Okay, and by trial and error method, you can have this as your Euler path. Now let's look at letter B. Is it possible for him to traverse all the trails and return to the starting point? Now take note, we will use now the Euler graph theorem. In the Euler graph theorem, in order for it to be Eulerian, uh, the vertices must have even degrees. All of the vertices must have even degrees. Take note, we have these two. Okay, they are odd. So meaning there is no Euler circuit on this graph. So therefore, the answer for letter B is no. It is not possible for the biker to traverse all the trails and return to the starting point without repeating any trail in the trip. Okay, so take note when we talk about Euler circuit, it is a closed path. It must start and end with the same vertex, traversing the graph without any repetition of edges. Okay, the same is true with the Euler path, but in Euler path, it it does not necessarily start and end with the same vertex.